The problem with games, and often even movie visual effects, is that they are digital, so they use simplified geometry that's often not quite good enough. It is reality, but simplified. For instance, if you zoom in on a real bread dough, you see small bubbles forming. Uh-oh, that means you would need to have bubble physics, which is incredibly difficult, if not impossible, to get right. Yes, real life is messy, and capturing that seems completely hopeless. Until scientists tried to write a computer simulation to do this 11 years ago. And this was the result. Wow! This is incredible! Beautiful water droplets merging and splitting. But it got better. Multimateria simulation of a bunch of melting bunnies was also possible. So why doesn't everyone just use this instead? Amazing quality games and movies await. Well, not quite. It has a big problem. When we give it larger scale scenes, it takes forever. Literally forever. Because the algorithm can hang and never finish. So, amazing research, but not quite there yet. However, it was so difficult to beat, we've been waiting for 11 years now for a research paper that could get the job done. It seemed like it would never happen. But now, hold on to your papers, fellow scholars, because it is finally here. Let's see what it can do. Holy mother of papers! A huge bunch of bubbles with 1,000 different materials. Yes! Each bubble is treated as a distinct material, not just some colored texture slapped onto it. And they merge and pop beautifully. But it gets better, because this is 2-minute papers, and it always gets better. Look, this is a simulation, so they also produced an opaque view of what is happening inside. And it is beautiful beyond words. Wow! It looks a bit like a molecular simulation. Loving it. Now, here's a crab. But you know what is better than a crab? Of course, 5 crabs. Let's throw them together. Now this is 5.3 million triangles and 72 different materials. Absolutely impossible to do. Now, we are going to cut through them and look inside and see if we get garbled up geometry or nice separation. And go! Wow! Look at that! Look at that! Goodness! This is cleaner than a freshly washed window in a Pixar movie. Now, you know what? Let's use this knowledge and observe this, what they call normal flow, where we blow things up. The spheres fill up the space beautifully. Now, the wireframe view reveals how difficult and complex this piece of geometry is. And now, what you've been waiting for. Let's do this slicing operation as with the crabs. And, whoa! The key part here is that the volume is under extreme pressure. It expands until it perfectly fills the space. And when we look into it, I see watertight geometry. No overlaps, no missing faces, no tears, and all this under extreme deformation. So, how on earth is all this possible? This looks like black magic. Well, this work is coming from Chris Voiton's group in Austria, and he is a master of fluids and topology. And the research paper explains it, but it is written for experts. I am not that. But I'll try to explain it in simple words. But first, listen, you'll love this one. To summarize, it replaces explicit collision-driven mesh surgery with a local implicit reconstruction step that converts self-intersections into topological changes. Okay, so what the heck does all this mean? Dear fellow scholars, this is 2-minute papers with Dr. Károly Zsolnai Fehér. Dr. Carol. So, previous work first. Imagine that you are making a movie where every time 2 bubbles touch, you stop everything. Take a pair of scissors, cut and glue everything together until it looks good. Then advance 1 pitiful frame and do it again. This is the collision-driven mesh surgery part. And no wonder it hangs when you give it a big scene. Okay, So, what the new one does instead is it creates a simulation that does not need cutting and gluing because, drumroll, it heals itself automatically and on the fly. Crazy! But wait, that means that you can even give it defective geometry, and it can not only deal with it, but heal it too. For instance, if you give it these poor little bunnies, their little rumps are going to get healed too. But it gets better. Oh, look! It finally runs in finite time. So, yes, it will be done within our lifetime. How cool is that? I'll tell you exactly how long it takes in a moment. Now, please drop a like, subscribe, and hit the bell icon, and leave a really kind comment to help save these papers because they are amazing. And absolutely nobody is talking about them. We, fellow scholars, have to save them. Okay, so in practical terms, it is 7 to 10 times faster than the previous technique. So, previously, an all-nighter render runs in a lunch break. Glorious! And it always finishes. Or otherwise, this would have to be an infinitely long lunch break. And it scales to huge scenes and broken geometries as well. It can handle bubbles bigger than the one inflating the AI stock market right now. Hooray! This is absolutely incredible, and it is going to change everything. You saw it here first on 2-minute papers. Now, not even this technique is perfect. It works with a sparse background grid, and this grid has a certain resolution, like pixels in an image, but in 3D. And if we have a hole that is smaller than our pixels, that is, one grid cell, it will miss it. If you catch it doing that, you can counteract it with higher grid resolution. And just one more paper down the line, I bet this also will be solved. A really advanced research paper explained in really simple words. What a time to be alive! So, this heals your meshes, no more craters. Subscribe to 2-minute papers. We need new tools for the era of LLMs, and Weights and Biases now has Weave, a lightweight toolkit to confidently iterate on LLM applications. Use traces to debug how data flows through each step of your app, and use evaluations to measure your progress. It is the best. Try it out now at wnb.me/papers or click the link in the description below.